Okay, so today we are going to talk about the three popular transformer, VIT, DeIT or DeIT, and SWIN. Okay, so this is called, the first work is a vision transformer. That was the first paper which applied transformer idea to the images. As we talked about last time, that transformer started from the NLP, natural language processing. The good thing about transformer is that it can be applied to images, or text, audio, any kind of modality. So the next work is called data efficient image transformer, DeIT or DeIT. And then the third one is the SWIN, which is called shifted window transformer. And all these three are, since the last year. So because that's one thing you want to realize, that deep learning moving so fast that it is, really impressive how the research is advancing. Okay, so vision transformer, it was published last year, iClear. It's actually less than a year, but it was on the archive in 2020. And this is the paper, and it already have 2,000 citation, which is pretty impressive. So and the title is, an image is worth 16 by 16 words, because as you remember that in the NLP we look at the words and sentences, and we talk about how we can do machine translation from French to English and so on. Now images are numbers actually, and visual information, so we need to kind of relate these images to words if you want to apply to transformer. So as we just discussed, that the main fundamental concept in transformer is the self-attention. Now we were able to explain self-attention, how attention is provided for a given word to the given word from all other words. In parallel, we get self-attention for all the words from all other words. Now, if we want to do self-attention for images, and let's say we consider an image, and each pixel we can consider as a word, then it'll be a lot of computation, because images are very large, right? Sentence can have 10 words or 30 words, but images have, millions of pixels. So that will be a problem. So what this paper does, logically, which is a logical thing to do, take an image and divide in pages. So each page is 16 by 16, and we'll consider that as a token or a word. And so now, in order to train a transformer well, we need a large data set, because as you recall that there are multi-head attentions, and there are different layers of transformers, and all those things we are learning. So there are lots of parameters to learn. So in general deep learning, that's a big bottleneck, that you need a lot of data. More data you have, better you can learn. So what these guys did, that he learned the vision transformer on this very huge data set, JFT. This is a Google data set, which is 300 million images they have. It's not public. And they got pretty good results, 88.5 on ImageNet, ImageNet Real 90%, and CFAR, pretty good results. And then VTAB, 19 different tasks, they got pretty good results. So what is the vision transformer? So what we do, we take an image and divide in these pages, and each page become a token or a word. And we just have projection here to change the dimension of each. We flatten this and become like a one-dimensional embedding, and then we plug in here. And these are the position coding And now we have one additional token, which we'll call CLS, or classifier token. And this we will randomly initialize. And then after transformer encoder, we will have the MLP, and we'll have these output, which would be different classes, like fully connected network, typically we have in the CNN also. So one thing you will notice when we talk about transformer, we had these two big blocks. One was the encoder, other was decoder. Because we are doing machine translation, we encode, say, French, then we want to decode and come up with English, or vice versa. Now here, we just want to solve classification problem. So we don't need a decoder, we just have encoder. And then this is a standard thing we have talked about. So we get the embedded pages, normalize multi-head attention, then skip connection, normalize MLP, and we can keep repeating this. Okay, so that was the vision transformer. Then we can go in detail how we divide an image in 16 by 16 pages. So typical resolution is 224 by 224. So we divide each page here is 16 by 16. If we divide 224 by 16, you will get 14. So we have these pages, 14 multiplied by 14, 196 pages. And then now each page is 16 by 16, but it's a RGB. So you have red, green, blue. So we will have 16 by 16 multiplied by 3. That'll be a dimension of each page. And we have 14 by 14 will become 196. We have 96 pages, 196 pages in the image. So, so therefore, we take each page and we take the 3 channels. So the dimension of each of the page, the embedding will be 768. Okay. And so this is these are the pages. So we have first page, this is this embedding, 768 dimensional, and we have 196 pages like that. Then we will have one CLS token. And so then complete VIT is image taken here, divided in 14 by 14 pages, each is 16 by 16. We get this thing, we do linear projection, and then we get, this is our embedding 768, and we have same position coding 768. And then we put this to the transformer encoder, and then we get the fully connected network, which will give us the after softmax will give us the which classes are present. So that's it. It's pretty simple, intuitive, and it works well. Are there any questions so far?
Professor?
Yes.
What do we initialize the CLS token with?
It will randomly, just initialize randomly, then it will learn. You would back propagate from here, the where last function is. So you learn that. Okay, so like, as you know, when you do the convolution, those weights you randomly initialize. Okay. Okay, so now this is what we do. So we have the class token, and these are the different pages, and this is their representation. And then we start from here, and then we have this recursion. We have different layers. So we take the previous layer L-1, we do the linear layer, and then multi-head attention, and then we do the skip connection, we add that, and then we will take that ZL prime, and we have MLP, as we discussed before, and then once at the end, we will do the last one, which will be the linear, the classifier. So that's very simple. And what they did, the VIT, they come up with 3 different variants. One they call base, other large and huge. And they have different layers. This is a simple one, 12 layers. You can have as many layers as you want. And then there's a dimension, as we talk about in this one, 768, but you can have more. And then you can have different heads, multi-head attention, and these are the parameters. So they got pretty good results, and they compare the results on these data sets, ImageNet, CFAR, and all those Oxford PATES and so on. And on these three versions, they got pretty good results. Now compared to the ResNet, these are the ResNet results, this is efficient net results, and that was the main thing. The transformer can work pretty well, and these are the how many cores and days they needed, so it wasn't that bad compared to, say, EfficientNet or the ResNet. Now, only thing here was that they used this the big data set, which is 300 million, and which was the problem. So and they show attention. They look at these different heights and average and different ways to show, and then this is really learning that attention is paid on this particular object here. And they have some more examples. I think here you can see here, and lots of these interesting results. For this one, this is attention, and for this one, this is attention, and so on. So again, I'm giving you like a very high level overview of these papers. Actually, this paper we are going to discuss on Monday in detail. So you will have some questions, and if you don't have time now, then these are the good questions to have. And as you read paper during the weekend, then you can try to find answers yourself. Otherwise, of course, we'll discuss paper in the class. This group will present, and then also discussion group will lead the discussion. So I think that's the idea, that because it's research paper has so many details, and this paper will be several pages. So it's not possible to know everything. Actually, it's good that you don't get all the answers from me. You discover yourself, and then that will trigger that you will have your own ideas. Okay. So this was the VIT. It's pretty nice and simple paper. Then let's go to the next one, which is the DeIT or DIT. I don't know, whichever way you call it. So this was training data efficient image transformer and distillation through attention. And this was published last year, and they already have 600 citations. So now the only difference between VIT and DIT is the training strategy and the distillation token. So we're going to discuss what is distillation. So in this one, so distillation is that you have the teacher, you want to distill the knowledge to student. Okay, so teacher is a much larger model, and student is smaller model. In this case, the teacher is CNN and student is transformer. So they show that you can do that, and it works pretty well. So so they use this distillation tokens. Remember that we have these tokens pages, and then we introduce a CLS token for classification. And but then these guys are introducing another token called distillation token, and that will be from teacher. So now that will give us attention between class and distillation token, and this actually give you competitive results, and this is convolution free transformer. And the good thing is that they are training on the ImageNet. As compared to the previous one, VIT, they were training on the 300 million images. ImageNet is only 1 million. So that's a big news here. And they can train on single computer in less than 3 days. And the it has 86 parameters, 86 million parameters, which is not that big, and achieve the top accuracy of 83% and 1 million with no external data. VIT was trained on 300 million images. Okay. So these are the three main things, as I mentioned earlier. So one is a knowledge distillation, and I think most of you should know that we want to, transfer knowledge from one model network to another model. So it's a pretty neat idea. I think Hinton came up with this. And then they have a regularization, so that model can learn, should not learn from data which is noisy, which is, regularization is a very common thing we do, and there are many different ways to do that. And then augmentation, a lot of augmentation, and that makes it. So augmentation basically is that you take an image, let's say you rotate, and you want to say, if it's an image of a dog, then rotated image of dog will be the same. So now you have two samples, or you can, crop part of it as still it's a dog and so on. So, so the simple, explanation of distillation. So let's say we have a one model, and we train to recognize, these cat images or dog images. And this is a traditional model. We do soft mix, we get these, we train it using cross entropy. We compare with the ground truth, what this predict, and we try to, minimize the cross entropy. So now what distillation does, that we have a teacher model. Say this is ResNet 101 and this is ResNet 18. So this is a much bigger model, it's expensive to train and so on. Now, since we have trained this, we want to distill the knowledge of this to the smaller model, so ResNet 18. And this is the way it works, that we get the teacher model, and which gives us this prediction, and we want to initialize this, the student model randomly, but we want to learn these parameters. When we do the distillation, this model does not change. This is frozen. So it will predict something, then we want to compare with what teacher is predicting and what the student is predicting. We want to make them similar. So that's basically is a distillation. Now, what they do here, so their teacher model is the CNN on Gen and ImageNet, and the student model is transformer. And so one thing they do, that they get output from the CNN model, and this becomes the distillation token. So they input that also in addition to the pages like that. And then they try to, minimize that difference. And that's the idea. So here is the DeIT. So this is the same thing. We have a class token. These are the pages in the image. And we go through these different layers, self-attention, everything. This is your classification token. But this is a new thing, distillation token, which gets out here. And this comes from the teacher. So you can, in principle, you can take this token and classify as we did before in VIT. You can do this one also, but they combine, they have lots of ablation and so on. So that's the main difference here. So they also have 3 different variations of this as VIT had. So, and they call it DeIT TI and DeIT S and DeIT B. And this is the embedding dimension, number of heads, number of layers, parameters, and running resolution and so on. So these are the, in a way, differences between VIT and DIT-B because they are same, similar size. So as you see that in VIT, we don't have much augmentation. There's no augmentation. And this is also these other things like the repeated augmentation and stochastic depth and lots of these things, level smoothing. But DeIT has all these things, and which is making much difference, augmentation, regularization. And we'll discuss again in detail on Wednesday this paper. So this is the performance. This is the top one accuracy on the ImageNet. And this is the images per second, how quickly, throughput. So this is the VIT-L, this is VIT-B. And so this one is the efficient net. And this one is with the knowledge distillation. As you see, with knowledge distillation, this gives better results. So then these are the more results on the different other data set, ImageNet, iNaturalist, and so on. And as you see here, that they can improve, it's 81, 83, 84, and so on, and similar phenomena in these all other data sets. So now they go through in detail, talk about these different things. This is there, and but then all other data augmentation, regularization, they go through which one really works and so on. So, so I think the one thing you have to keep in mind that they have this additional knowledge distillation. So this assumes that you already have trained CNN, even though CNN is trained on the same ImageNet 1 million. So then they treat that as a teacher and then distill the knowledge from there to transformer. So still, if you look at, from the number of data, the size of data, which is good because only 1 million and the VIT uses 300 million and performance good. So this knowledge distillation and all different augmentation, the way they train and so on, it makes a difference. Okay, so then the third paper, this again came last year. And this actually won the MAR prize. Now in computer vision, the most prestigious award you can get, best paper award, can get the MAR prize. That's the ultimate. And so David Marr, was a very famous researcher, and most of the work we are following these days, after his work in 1980s, is kind of following his approach, which is called computational vision, that he talked about. You have to define what the problem is, come up with the approach, and then implement and so on. So Marr was a neurophysiologist, and he came from England to MIT, and he wanted to use some of the ideas in neurophysiology to solving computer vision problems. And he did a lot of interesting work at MIT, but unfortunately he passed away, very young, 35 years old. And he's a very nice book called Vision. So if you guys are interested, it's a very general book. I think everybody doing research in computer vision should read this book. It's very, very general. It's scientific American level language. Don't need a much knowledge, but it's a pretty enjoyable book. So these guys, got a smart price last year on this transformer. So as you can see, the transformer is becoming so important in computer vision research that you can get a most prestigious prize. Okay, so SWIN is stand for the the window. I'll talk about that. The adaptive transformer. So as you know, that we have used a transformer for the language. It started the first paper. Attention all you need was from NLP people. They wanted use for machine translation, and so people started using transformer ideas in computer vision. And as I mentioned, the main problem transforming transformer from NLP, from language to vision, the problem has been, one is that we have a lot of data, because the images, so many pixels, million of pixels and so on. And also images has a lot of scale variation. There can be image of a dog, but can be very small, can be large, and it's much more complex. But when you have text, word means that is, when you spell dog, D-O-G, that's it, dog is dog. So that is the complication, that vision is such a hard problem. So large variation in scale of visual entities. Second is, as I say, about the high resolution image and a lot of data. So to address these differences, they propose a couple of interesting ideas. One is the hierarchical transformer, whose represented computed with shifted windows. So SWIN is from shifted window. So this self-attention will be a local, not the global as these other transformers are using, but still it works pretty well. So shifted window limit attention to local windows and also allow the cross window connections. Okay, so and it again, see any paper you will read in these computer vision, deep learning, AI in general. So the important thing is that you have to beat the state of art. Otherwise, they are not going to look at it. So first, you have to have on benchmark data set better results than any known method. Then they will look at, say, well, what's new? You can have better results, but if your method is ad hoc, bunch of combination of different things and so on, it's not well written and so on, you won't get accepted. So, so in this paper, as you see, that they have a new idea that they want to do attention in the local window, and then they want to look at a hierarchy, so that is a novelty, and the results are very good. So they can get the results 87.3 on ImageNet. Then not only classification, but they can do dense prediction, such as the object detection, and they also have very good results on that, as you see, and semantic segmentation. And so it surpasses the previous state of art by 2.7% and 2.6% on the COCO, and 3.2 on this data set of semantic segmentation. So the main point is that in VIT, as we saw, that the size of this page is fixed, all these levels. So it's 16 by 16 like this. And what they are doing in SWIN is this page size is varying. So they start with 4 by 4, then 8 by 8, 16 by 16. So this is the window. So that's a hierarchy. So that is making a difference. So just to go in detail, so they start with an image, H by W as usual, 3 channels. So you partition image in pages as we talk about, and each page is 4 by 4. So we will have these many pages, and each is 3 channels. So 4 by 4, 16 multiplied by 3, so 48 dimension of each page. Okay. So then we look at the stage 1, and we take this to the linear embedding and the SWIN transformer block. So we'll have 2 copies of this. And what comes out is, again, these many pages, but here we'll have C, which will be fixed, and I'm going to tell you what that is. And then we will have another stage, again, page merging, SWIN transformer, 2 blocks of that. And then now, as we talk about, then we will change the size of the page. So now we will have 8 by 8, and we'll increase the size, will increase because we are making a bigger page, so it's 2C. Then we will have third stage, again, page merging. The smaller page will become bigger pages, as we say. And then SWIN transformer, 6 blocks, and then we will have now the number of pages will reduce because we are dividing by 16, and then we'll increase the size of the page. Then stage 4, so we'll keep doing, and here we will have divide by 32. So that's it, so that is the SWIN transformer. So 4 stages and different blocks. Now, these are the 2 successive blocks. So we take these pages from the previous level, L-1, linear, layer, then multi-head attention, windows. So the attention will be local in that particular window. I'll show you in figure again. Then we'll skip connection, then linear layer MLP. Now this is first block. Then we will have this one here, which will come out here. In this block, again, linear layer, but this is a shifted window. We'll have the overlapping window, multi-head self-attention, then skip connection, linear layer, MLP. And that's the idea. Okay. Yeah, so let's go through that and we'll come back to this. Okay, so this is the layer 1. And as you see that we have here 4 by 4 page. Okay, these are pages. Then when we do the layer 1+1, then we are taking this overlapping shifted window. So here we have window like this, then we shift halfway, now it becomes like this. So that is what the page is. This page is small page here, and the local window perform the self-attention. So if you go back to this one here, that this is a standard one, but the only difference is that when we do the self-attention in the traditional one, we are going to do the whole image. But here we are going to do only local, as what's clear from this figure here. So the traditionally we will do the self-attention in the whole token, and it was 16 by 16, and we will take this video token, and we will have this attention to that, and then we'll have all those. But here In the SWIN one, we are just doing the local attention only in this one. We won't look at these other ones. So that is one difference. But now what they are doing, in order to capture the look at the neighboring one, so they will have two blocks. We do the self-attention here, and so on. Now let's take the window, move it, put it here, and then we get a shifted window, which is this one. And part of in that shifted window, we get the attention of these pixels to these pixels. So that is one difference, and somehow that makes a difference. And that is what we have here. This is very standard, okay? And it's a window-based self-attention. And but then once come out, then we do the shifted window, as I explained that. And they have different versions of that, and we'll discuss that in, a week from next week when we go in detail. So that's the main difference, and this is what is explained here, that we take the previous representation from L-1, the linear, then we do the multi self-attention window and the base of window, we do the skip connection, and then we take this one and MLP. This is our first block here. Then second block is that we take the ZL and we do the shifted window multi-held self-attention, and then we take this one and the linear MLP. So that's the main difference. So again, in this one, they have different versions, T, S, B, and L, and this is the C. So as was this, C is 96, and then when another C for this version is 128, and for this version 192. And these are the different layer numbers. As you remember, there were 4 stages. Within that, we can have different blocks. So you have 2262, and this one have 18, and all these different configuration which they are doing, and it works pretty well. This is a comparison between the DeIT and the SWIN. As you see that they get better results, not that much, but still better distal ImageNet. Main thing they have the difference which is making, and this shows you the throughput flops and so on, in comparison with also ResNet, is that this works also for the object detection. So these are the results on mask or CNN. And these are pretty good results. As you see, there's a big difference in these different performance. And these are results on semantic segmentation. And these are also pretty good improvement as compared to these other ones. So in summary, we talk about very quickly, VIT, that's a first vision transformer, and trained on the huge data set of 300 million images. And then extension of that for the data efficient transformer. The main concept there was that you can use a knowledge distillation from CNN train and augmentation efficient training strategy. And good thing was that they were able to train this on ImageNet only, 1 million compared to 300 million. And then we had the SWIN transformer, which has a window attention to reduce the computation, but then they have shifted window also. They have 2 blocks. And the good thing was they had very good results on object detection and semantic segmentation. So I think this is the end of the lecture, and we are a couple of minutes late. So we will end it here, and then we'll upload this